recording? Yes. Okay.
So, I want to start with f of x equals 1 over x. It's one of those really weird functions that a lot of what you can tell me about this graph tells you more about what's missing than what's there, right? Our domain says that x can't be 0. Our range says that y can't be 0. That's not helpful to me to know what I'm actually supposed to look at when I'm looking at 1 over x. Right? It tells me what I'm not going to see. I'm not going to see x be 0. I'm not going to see y be 0. I can think of a lot of graphs where x is not 0 and y is not 0.
I lost my pencil.
Oh, okay. I have extras. Funny, because I was just trying to find one instead. Okay, and even saying that f of 0, what's f of 0 on this? What's undefined? That's not helpful to me either. There is no value at 0. Okay? So the function notation that you guys came up with in Algebra 1 is not enough to get you through what you need to in order to talk about your graphs in a functional way. We need more language. Okay, that's where limits are going to come in. So f of 0 being undefined, that's fine. Okay. When I say x can't be 0 and that f of 0 is undefined, how many values can I not plug into this function?
2. Wait, no. 1.
Just one value at x equals 0.
Yeah.
How many other values are there?
Infinite.
Infinitely many. So there's infinitely many places where this function is defined. Okay. What's the first point after 0 that this function is defined at?
0, 0, 0, 0.
It's not 1? It's not like f of 0 is undefined, then f of 1 is 1?
Yeah.
And that's like the points next, right, next to each other?
Yeah.
There's values in this.
How many values are in between?
Infinite.
There's infinitely many values in between here, right?
Yeah.
Which is part of the reason that this language of f of 0 being undefined is so incomplete. Right. And I could plug in numbers, right? I could do f of 1 would be 1, right? 1 over 1, which is 1. And then f of 2 would be 1. I don't want to do 2. I wanna get close to I want to get close to 0. I want to know what's happening, because if there's infinitely many values in between 0 and 1, I want to talk about what they're looking like. Okay? So if I do f of a half, I like fractions better than decimals every time. Why is that?
They're exact.
Because they're exact. Fractions are exact, decimals are approximations. Okay? So I'm going to do 1 divided by half. What's 1 divided by half?
2.
2. So I got that point. And then if I do 1 divided by, I want to get closer to 0.
4.
Okay. Let's do like a tenth. That sounds like fun. Doesn't it sound like fun? So 1 divided by 10 is 10. I'm going to do 1,000. That's like getting up there, right? So f of, it's up there, and then f of 1,000th is 1 divided by 1/1,000. And 1 divided by 1/1,000th is 1,000. Okay, so I can see, describe what's happening here.
It's going towards the y axis function.
It's x decreases
X
y.
goes to 0, y goes to
X decreases y.
Okay, so I'm approaching 0,
Then y is
but that's even not a complete description. Okay, I'm on the right side of 0 right now to be approaching 0 and be talking about what we're talking about. But what if I was standing on this side of my function? Am I going to have the same values that I'm approaching?
No.
No. Okay. How do you want to differentiate between this side of the function and this side of the function? I'm recording right now. Can you hear me? Can you come back later?
Yeah.
All right, I'm doing awesome.
Positive x.
Okay. Kind of. And in this particular case, that's a sure bet. But if I shifted the point where I'm talking to approaching to like 10, then I'm going to have positive numbers on both sides. So I want to give a little bit more of something that will work in multiple situations instead of just fitting this particular situation. Right? We're developing new language. This is why I keep equating it to language, and it really, really is, guys. instead of approaching the funny spot is at 0. Over here, I'm talking about, I feel like Vanna White, except she never spins like that, right? She should. Okay, we'll send her this video. I'm approaching from this side, from the right side. It's a good rate, and even if it was at 10, I could approach from this side or from this side, and it's a left side, right side. So let's say as x approaches 0, from the right of 0. What are my y values doing?
Increasing.
Approaching
Y approaches infinity.
Y increases. Y, I don't even like that word. Y gets bigger and bigger positive values without bound. Okay? Alright. And that's really the language behind here, but that's like kind of bulky. And I know you guys are, well, just like, you know, the old dudes from math, very efficient with your time. Is that a nice way to phrase it? Okay. And they're like, this is too much to write. Okay. And in Algebra 2 and Pre-Calc, you guys streamlined that a little bit. And you wrote a little more briefly as x approaches 0 from the right. Right, we use a little positive sign for that. And that's why some of you guys were saying from the positive side of things. Which is, but that means from the right. Okay. My y increases without bound. It gets bigger and bigger and bigger and bigger and bigger, positives. That means that y is approaching what we call it? Infinity. Okay. So we know f of 0 is undefined. Is infinity a value?
It's a amount
No,
of numbers.
it's a number you cannot approach.
It's not a number I can't
I mean,
approach
no.
because that suggests that it's a number. It's not a number.
Yeah.
It's the what?
The amount of numbers.
The what? I didn't hear you.
The amount of numbers.
It's not an amount of, it
The
can't,
range.
okay, it can't be an amount, it can't be a value, it can't be a number because it's none of those things.
It's a word.
It's an idea.
It's something endless.
It's a concept,
Ah.
okay? It could be like,
It's something endless.
it's the concept that something is getting, in this case, bigger and bigger and bigger and bigger, right? It's not that f of 0 equals infinity. That would be an incorrect statement. But as x gets closer to 0 from the right of 0, the y values are going to get bigger and bigger and bigger. That's what this says, even though I don't have to write out all the language to it, okay? And then they got even smarter about it, and all these three things say the same thing. And you guys were introduced to this limit notation in pre-calc. So we write the limit as x approaches 0 from the right of the function 1 over x is infinity. Okay? And this is language for what happens to your function as you approach a certain value. And I can go back up here and I can graph that piece of it. Right here. Okay, and if I approach 0 from the right, my y values are getting bigger and bigger and bigger, and that's what this limit says. I can never plug in 0 to this function because the function's undefined at 0. Okay? I never reach a value of infinity because infinity is not a value. It's the concept that it gets bigger and bigger and bigger. But that's perfectly explaining what's happening here. Okay? And that's our new language of limits. So a little definition for us. Okay, and you guys are going to have to get used to putting definitions and theorems into your notebooks. Okay. The limit as x approaches a of f of x equals L means that we can make f of x get closer and closer to L by taking x sufficiently close to a. Okay? All right? We don't want to be ambiguous in our language here. We're not writing poetry. Okay? I'm not trying to use fancy math language to intimidate you. This is like very straightforward language here. But that's what that limit means. That you can get your function closer and closer and closer to a value, or not a value in some cases when you've got infinity involved, by getting your x coordinate closer and closer and closer to that number in question. Okay? So let's look at some examples. Okay. Let's look at this function. Isn't she pretty? Okay, there's my function. Okay, I want to know what is the limit as x approaches 2 of this function. Okay, and it's essentially saying like your graph is a road map, and if you're traveling along that road towards an x coordinate of 2, right? It says limit as x approaches 2. What are your y values approaching? What do you guys think? 3? Agree? Disagree? Agree? Right, if this is my map, okay, you guys have to understand that when you're talking about a graph and you're talking about when, where, the locators are your x coordinates. So you're letting x approach 2. Here's 2. You're letting x approach 2, but on the graph. So on the map, here we are approaching 2. An x value of 2. And my y values are getting closer and closer and closer to 3. Do they get to be 3?
No.
Do my y values get to actually be 3?
Yes.
Yeah.
Yes.
Yeah. So how do I write that the y value at 2 is 3 in like a cute short way? How do we write that? We have notation that you guys found out in, or that learned in Algebra 1 to say that at 2, when x is 2, the y value is 3. Cute little way to say that.
2, coordinate.
Okay, I can write a coordinate.
As x approaches 2,
Simple.
f of 2 is 3.
F of 2 equals 3. Okay? This is saying the point 2, 3 is on my curve. That's not what I'm interested in here. I'm interested in limits. Okay? So I'm interested, this top line is saying that as you approach an x value of 2, the y values are approaching 3. The bottom line says that, oh, there's the point 2, 3 in your graph. Okay? On this one, here's another function. I want to know the limit as x approaches 2 of f of x. Isaiah, what do you think? Okay. I just was talking about a roadmap. Okay? So if this is your roadmap, and you're going to follow along towards x equals 2, the question is, where are you heading? You're doing away. You're going this way. Okay? When you guys are doing limits, you're playing the I'm not touching you game. Okay, Casey, can you come up here for a second, do you mind? Alright? And this is the best way for me to model this for you guys. Hopefully you have, at least at some point in your life, played this game with somebody. Okay? The limits are when you get closer and closer and closer. So we play I'm not touching you, but I'm not touching you, 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 right? There is nobody in this universe that plays the I'm not touching you game this way, right? You would like just laugh at Kelly if she did this to you.
Oh, yeah.
Right?
Except it's the opposite.
I'm not touching you, I'm not touching you, I'm not touching you. Well, yeah, you're right. You're not touching me. Right? That's not what we're talking about here. But it's a natural instinct, thank you. It's a natural instinct for you guys to think that way because you're like, when you see that 2, you're instantly at 2, and you want to move. But you want to get near 2 and get closer, okay? So if I'm going to play that I'm not touching you with 2, where is my road taking me? 3. Okay? It does not matter that somebody built a wall around it and you can't get in. That's not what this notation is asking. This notation is asking, where are you headed? And if you approach an x-coordinate of 2, your y values are approaching 3. Okay? What's different about the value of the function at 2 on this one from this one?
That has open circle.
Open circle.
Undefined.
Okay, so what do we say? F of 2 is what?
Undefined.
F of 2 is undefined. Okay? That won't affect the limit because the limit is saying what value are you approaching, not what value do you take on. That's notation that you guys established in Algebra 1. What value does it take on is the notation from Algebra 1. This is new notation to say, oh, I'm approaching this value. All right. Next one. Okay. I want to know what's the limit as x approaches 2 of f of x. And since you guys are interested, you guys are already done?
No, we don't have a bus, so we're back. No, they took half the band and they left.
Guys, just have a seat. I don't know we're recording this. Okay, so limit as x approaches 2 of f of x is going to ask you, where is your roadmap telling you to head?
3.
Casey's saying 3. Agree or disagree?
Agreed.
Okay? If I hand you this map, and you're traveling along towards an x-coordinate of 2, you're headed towards the magical land of 3, right? You're headed, somebody built a wall around it, you can't get inside. Okay? I don't know who would do that. F of 2 equals what? 1. Okay? The fact that this is some like magical land where you're on your road to x equals 2 and you end up by magical 3, you can't get inside because there's a wall built around it and you get magically transported to it doesn't even matter. Oh, what stupid story there is about this roadmap. But the fact that there is a different value here has no impact on this limit. And that's what you guys need to understand. The language of limit is asking you where are you headed, not where do you end up, but where are you headed. I'm headed towards 3. All right. So I gave you guys 3. They're not crazy different, but they are distinctly different. The value function matches the limit. You're headed towards, you get to actually, I just call that ET phone home. Right? Have you guys seen ET? Okay. So they get to ET phone home, and then they actually get to phone home. There's no difference between like getting close and getting to achieve. Okay? So how am I going to make it so that we have trouble talking about the limit? Like, how can I break this graph and make it not have a limit anymore? Liza?
Piecewise function?
Okay, I don't want an actual equation. Like, I didn't give you the equation of any of these. I want to know graphically, what do I have to do to this to make it so that we can no longer answer that question of what's the limit?
Domain restriction?
I just want to change the picture, okay? I don't want to get on the level that you guys are getting at because that's unnecessary information for us right now. I just want to know how do I have to affect this picture so what do you guys think Faiza's suggesting when she's saying a piecewise function?
Add another function to this graph.
What do you mean another function?
We write at x equals 2.
Okay, I'm not writing anything.
Okay.
Just like separate.
I want to draw a picture. What do you mean separate it?
Like, make it, like, not like that, like, just, I don't know.
Yeah, we're
I
together-
see you guys.
we're
Okay,
together
I
as a
do.
whole.
Okay. What, like, draw in the air for me then. Somebody draw in the air for me what you guys think needs to happen with this graph in order for, or talk to me about conceptually. What don't we like about math class that you can have in most of your other classes? Statistics, English.
Words.
The words are here too. Okay, we need words because we need to be able to communicate math. Okay, if we only know math and can't communicate math, we are useless, to be perfectly honest. Okay? So I need you guys to get comfortable being uncomfortable trying to figure out how to communicate math. Okay? I want to break this picture. So, okay, so aside from words, what else do we not like in math? Like, what do you, let me ask this question. What do we like about math?
It makes sense.
It makes sense. Okay, well, why does it make sense?
Because it is
It's either right or wrong.
It's either right or wrong, right? Okay. It's either right or it's wrong. It's either good or it's bad. It's either exact. We don't do ambiguity. Ambiguity. Sorry, that was like a great pronunciation of that. We don't do ambiguity in here, right? If it's ambiguous, what do we say? It doesn't exist. Okay? So how can we make my map ambiguous? How can we make it not black and white, right or wrong? What can I do to break this picture?
You get rid of the hole, and you put dots where the hole should be, like 2 dots. No, like that's where the lines, and if there's no hole, like they still keep going. But doesn't touch.
Oh, you want this to be like this?
No.
Okay, good. 'Cause
Two of
what's
those.
wrong with that?
Two of those.
That's not true.
Back to
Like
back.
here?
No.
Okay.
Like, the 2 lines, you see where the holes should be? So can you erase what you
Oh,
just
so
did?
like on the edges of the lines.
Alright, at the end of the lines.
Mm-hmm.
No, you made a hole.
No, okay, so erase the circle.
Alright, now.
On one line, on the
Make a-
top line, at the very edge of it, put a
Put a
whole
dot.
circle.
Yeah, it put 2 of those and they're touching each other. They're actually touching. But
Wait,
it's not
down
at 2.
below.
That's not
I know, I was just trying to.
Okay. Let's put my hole back.
No, I thought that.
Okay. You can't have more than one point at one value because it's not a function. So you can't have like, okay? It's an abstract question I'm asking you guys. But I want to know, when is the map gonna fail me? Like if I ask you to, like on any of these maps, if I say, go ahead towards, at x equals 2, be in the right location, follow the map, and when you show up, you'll get an A in Calc. But if you go to the wrong spot, you're gonna fail, okay? So I want you to head towards the right spot. On this map, you can head towards the right spot, right? When x is 2, you're at the magical land of 3. When x is 2, you're heading to the magical land of 3. When x is 2, you're heading, or as x gets close to 2, you're heading to the magical land of 3. Okay. I don't want to do asymptotes. We had the 1 over x up here already. A simple way to break this graph.
If they're both approaching a different number.
This is doing this. Okay. Has anybody ever like tried to high five somebody and you just miss?
Oh, yeah.
That's a failed high five, right? That's like ET not going home. Okay. If you're going to 2 different directions, that's a bad map, right? If I give you this map, I can even just take that and then take that from before and just have this go there instead. Or I could have it go up or something. I could do it whatever I want to do it. It's still a function, right? I haven't broken any rules of math. That's a function. Okay? Yes, it's a piecewise defined function. I'm not interested in that part of it right now. Okay? But if I ask you for the limit as x approaches 2 of f of x, I'm asking where do you head, if you head towards an x coordinate of 2, where are you heading? Where do you go?
3.
Monica, where do you go? 3. Okay, Monica says 3. Harsh, where do you go?
1.
1? Who's right?
Or,
They're both.
They're
They're both right.
They're both wrong. Or one of them's right, but who? Do we like that feeling in math?
No.
No, we don't do that. So on this, we say, that's a bad map. Limit as x approaches 2, that's not going to exist. We can either write D and E or undefined. Okay. What's the problem with this one that's not an issue with these other 3 ones that are kind of peculiar?
no matter where you start from, on the other ones, you'll end up at the same place. This one, it depends on where you start from.
Depends on where you start from,
Yeah.
okay? So if I start from this side of 2, how can I, what side of this is this of 2?
Negative.
The left side, okay? If I approach from the left side, what do we call that? Oh, okay, so if I approach from the left, it's not just a limit, it's now a, we qualify the limit?
Sure.
Alright, just for a second. If I approach from the left of 2, I'm approaching what y value?
In 3.
3. If I approach from the right of 2, what y value am I approaching? 1. What do we call that approach, the I'm not touching you approach? You guys need to
Limit.
try a
Limit?
little bit harder. A limit. It's a limit. Okay? Okay. Alright, I'm gonna silence the one student who keeps answering questions and give you guys more opportunity. But it's okay to say the wrong thing. It'll get us to the right point, but saying nothing is not helpful. Okay? Alright, so let's qualify it now. Let's put those two concepts together. So we talked about approaching from the left and approaching from the right. And then we called the approach what? A limit. So now, what can we call it? Approaching from the left, we're now going to call what? What kind of limit?
Negative. Or
No, it's not a negative limit. There's no such thing as a negative limit. A limit can have a negative value, but there's no such thing as a negative limit. Instead of calling it approaching from the left, if the approaching part is called a limit, we can then qualify it as a, 2 words. One goes here, one goes here. Wonderful, a left limit. Right? This is not a difficult.
You're giving us trick questions.
I'm not giving you trick questions, I'm asking you basic questions to follow along. I'm not being, like, we're talking concrete here, okay? So my left limit is 3, right? I'll just say that is 3. My right limit is what I call it when I approach it from the right side. My right limit is 1. And I don't like that these don't match. That's a problem. Okay, they need to match. If they match, it's a good roadmap. Here, if I approach an x-coordinate of 2 from the left, I'm approaching a y value of 3. If I approach it from the right, I'm approaching a y value of 3. Okay. On this one, if I approach an x value of 2 from the left, I'm approaching a y value of 3. If I approach an x value of 2 from the right, I'm approaching a y value of 3. Okay. And approaching from the left means find your number, get on the left side of it, and then go towards your number. Sometimes that confuses some students a little bit because I'm not moving in a leftward direction. But I'm getting on the left of it and then going towards it. Okay, it's a left limit is a left approach. Okay, if I approach from the right of it, I'm approaching a y value of 3. On this one, if I approach from the left of it, I'm approaching a y value of 3. If I'm approaching from the right of it, I'm approaching a y value of 3. On this one, if I approach from the left, I'm approaching a y value of 3. On this one, if I approach from the right, I'm approaching a y value of 1. That's not a good map. It's not a good rule. Okay, so what we say is the limit doesn't exist. Alright, so we have a theorem that goes along with that. Well, first of all, let's define left limits and right limits. And we got some of this notation out already. Okay. So a left limit, you guys can abbreviate it LL. Did any of you guys leave for this block? Like nobody band or cheer left? Or did some of band and cheer leave?
Like 20 band students left.
Yeah,
and
half
one
of
really
band
left.
left, and then I think they're coming back.
Okay,
I'm not sure.
just wanted to- So left limit, the way I write that is I write limit as x approaches my value. And instead of having to write out the words from the left, what do I do? A little negative sign. So you guys are drawing in the air. Okay. It's It's always gotta be the limit of something. You can't have the lim without it being of something. It says the limit of my function. That's how I write my left limit. My right limit. Alright, and just to clarify, this means that we're going to approach from the left of A. From the left of A. My right limit is my RL, totally fine abbreviation. If you write, probably, like on my tests, quizzes for sure, LL, I recognize that as a left limit. This G money too. Hey. I know, I have it. I'm just recording a lesson right now. Bring it up. Okay. Oh, let me just get back to my lesson. I'm sorry. Bye. Okay. I don't know what I was saying. Oh, if you write on my quizzes or my tests RL, LL, fine. Okay? In college calc, fine. On AP, I might go and actually, just to make sure, write left limit, but LL and RL are pretty universal when you're talking about limits. Okay, it's not a my notation, it's a universal notation. And if I want to approach from the right, I'm gonna write x approaches A with a little positive sign. And this is again, approaching from the right of A. Okay, so that means you get to the right of A and you get towards it. This J1A too. I'm in the middle of recording a lesson. Can I just get back to it? I'm sorry. Thanks. I don't know who that was. Okay. Can I put like a do not disturb on my phone? Okay, and then we have a theorem. And we're gonna talk theorems and definitions and all that kind of good stuff here. And I want you to get used to that because if you take any college math classes, you're gonna get a lot of that. Okay, my theorem says that if the limit as x approaches A from the left of f of x equals the limit as x approaches A from the right of f of x equals L, then the limit as x approaches A of f of x equals L. Alright. So part of the battle, and this is part of the reason I was showing you guys some of my college notebooks, is reading math speak and turning it into English. Okay? That's important. To be able to read math and make it say words in your head. So what is this theorem saying?
It's saying, if
Yeah.
if the limit from the left equals the limit from the right, then the limit equals up.
Yeah, okay? So a limit's gonna exist if the left limit and the right limit are heading in the same direction. Okay? Alright, so make yourself a note if you need to on that. But that's what's going on then. Okay. I'm gonna give you guys some properties of limits that'll play in. Just got them in your notebook for now, and we'll see how they play in, but don't stress about them right now. If I have the limit of a sum or difference of functions, you're just going to do the limit of each one and either add or subtract them based on what you're asked. Okay. This is a helpful property when sometimes limit of one function gets too convoluted, or like the big function is too convoluted, so you look at the individual pieces and then you can put them back together. If I have the limit of a constant times a function, it's just going to be the constant times the limit of the function. Okay. Okay, so based on that example before, where we had the limit as x approaches 2 of f of x equaling 3, then the limit as x approaches 2 of negative 4 f of x is going to be what? Negative 12. Negative 4 times 3, which is negative 12. Okay. What else? Let's see. If I have the limit of a product of two functions, and you'll see this on a homework this next week, not this weekend. Right, if I have a limit of a product of two functions, it's going to be the product of the limit of the functions. So I could take the limit of the first one and multiply it by the limit of the second one. Okay, and again, that's when you have some crazy mother functions and you don't know how to deal with them and taking the limit of all of it. So you look at the components and then you piece it back together. And then the last one is for quotient, so that the limit as x approaches a of f of x over g of x is going to equal the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. Okay? I don't think you're going to be needing these properties, particularly for our homework tonight, so if it's feeling uncomfortable, just wait until we apply it to something, and then it'll make more sense. And this is so long as the denominator is not 0, right? We always have to say that whenever we have a fraction. We'll be like, wait a second, just to cover your butt, we're gonna make sure no denominators are 0. No animals were harmed in the making of this calculus lesson. Right? Because if we let the denominator be 0, the whole world implodes. Your limits are actually really smart. And I erased a lot of these pictures, but the most common situation that you guys have when you are working with the functions that you've worked with in the past is almost everywhere your left limit and your right limit are approaching the same thing and actually take on that same value, right? Like all your lines, all your parabolas, all your cubics, all your sideways parabolas and your semicircles and your exponentials and your logs and your trig graphs and what am I missing? All those functions that you guys graphed, they're mostly continuous, right? We've graphed a couple discontinuities, we've seen them on all kinds of functions. That was funny places. Somebody said tan. What's up with tan? What does tan have? First of all, it's not tan. What is it?
Tangent.
It's either tangent or it's tan of x. Oh, you shouldn't even say tan of x. You should say tangent of x. Okay. What's happening on the tangent function? You got asymptotes. Okay. So then you got some weird behavior. What other kinds of functions give you weird behavior? Rational functions. Somebody said rational functions, which give you asymptotes. Tangent is a type of rational function. What does a rational function actually mean? A fraction function, right? Ratio is a type of fraction, and I guess some person at some point decided if we kept saying fraction function that maybe another F word would slip out, so we call them rational functions instead. Okay? One other type of function where I get funny stuff happening that's abnormal.
Inverse functions?
Let's not deal with that in a second.
Cotangent?
Piecewise. Cotangent is just another rational function. Okay, piecewise functions, we get some funny stuff popping up. But for the most part, our functions are really good at telling us, and our limits are really good at telling us if something is weird going on. Okay, we are going to make a list of how to find a limit algebraically. Okay. And I would suggest just making a spot at the top of your next page and having this be your list, and don't write anything else on that page because we're going to keep adding to it. Today, Monday, Tuesday, we're going to keep adding to it. Okay. You guys are asked to find the limit. Like, for example, we're going to find some limits. Are you guys excited? You guys sound really excited. Like you're so excited you can't even tell me how excited you are.
Yay.
Okay, so we're going to find the limit of been chicken scratching this limit as much as I can. It's an LIM for limit, limit, okay? The limit is big, the stuff underneath it is not, it's small, and it's underneath the limit. Next to it, I have my function. Okay, why am I talking about this like this? Because notation is important, consistency is important, everybody writing their limits the same way is important because it's a math class, let's face it. Okay, and you need to represent your work properly. So pay attention to my notation. I'm not making up my version of things. If I do, I'll tell you. Like, this is how I do it, but no, that's how you write a limit. It doesn't matter whose classroom you're in, who your calc teacher is, what state you're in, what country you're in. That's how you write this limit. How am I going to take this limit, do you think? What's the function? What's the function, guys?
Parabola.
You got parabola, right? Is there anything funny happening on a parabola?
No.
Are you going to get to ET phone home?
Yeah.
Yeah, because on a parabola, like anywhere you go, if you approach the left and the right, you're actually going to meet that point, right?
Yeah.
Okay. So how am I going to find this limit?
You just plug in one.
You just plug in 1. Okay. So we're going to plug in. That's my first step. Okay. If you get a number, you're done. Thanks. If you get a number, you're done. Okay. I'm just recording this. Okay. So I'm going to plug in. So I'm going to have, and I don't really need to see this, but this is what I'm doing. I'm going to plug in 1 for x. So 3 times 1 squared minus 4 times 1 plus 8. And I get 7? Yes? Agree? Disagree? 7. Okay, that's my answer. Okay.
No, my math is
Okay. What's that mean? I have a parabola. And what does it mean? As x approaches 1, the y value approaches 7. So you probably have a 0.17 on your graph, probably, right? Okay. All right. Do, for me, the limit as x approaches 3 of the square root of 9 minus x squared. What do? I plug it in. Isn't that like a Glade plug-in commercial? Plug it in, plug it in. Well, I have an amazing singing voice. Okay, so what am I getting here? 0, fantastic. So if I approach 3 on this cute little, what kind of equation is this? A semicircle, thanks. Okay, I'm gonna get 0 for, I'm gonna approach 0 for my y value. Let's take the limit as x approaches 0 of x to the 4th minus 5x plus 2 over x minus 1. I'm just gonna plug in my number. If I plug in 0, that's wonderful. I love plugging in 0. I get 2 over negative 1 is negative 2. That's my answer. What kind of function is that one? It's a rational function. It's probably a little bit asymptote action going on in there, right?
Okay then.
What? You guys don't get excited about graphs that have asymptotes? I do. Okay. So I have an asymptote going at x equals 1, right? Right? Why is it at x equals 1, guys?
Because it's undefined.
Because that's where the denominator is 0, right? Okay. It's not a 0 for the numerator, it's just a 0 for the denominator. So I have an asymptote at x equals 1, but if I approach 0, that has nothing to do with the asymptote at x equals 1. How many points are there between 0 and 1 on this graph? Infinitely many points.
Yes.
So something weird happening at 1 is not going to affect a limit at 0. Okay, let's do, oh, I know you're going to love this one. You guys ready? Okay. Let's take the limit as x approaches pi of cosine of x. Okay. Trig is not going anywhere. So if you think you don't need to know your trig values because clearly according to your test you don't think you need to know your trig values, you need to know your trig values. Cosine of pi is not 1.
Negative
Okay, thank you, it's negative 1. Okay. Sorry for my sloppy limits.
It's okay.
Okay, I'm going to take the limit of x squared minus 4 over x minus 2?
Undefined.
Undefined.
No.
Okay. Why are you saying undefined initially?
Cause the bottom's 0.
Okay, a bottom being 0 is not enough for me to say undefined.
You can't divide by 0.
Oh, 0 over 0.
I get a 0 over 0 very specifically in this particular problem. There's a big difference between having a number over 0 and having a 0 over 0. Okay? Very different things happening on your graphs. Okay? This function, this wonderful rational function, is undefined at x equals 2. But a limit can only be undefined when what? We need to be a little bit more specific in our language. When you approach two different spots. From where?
The left limit and the right limit.
From the left and from the right. If the left limit and the right limit are not the same, that's when I have an issue. Which requires us to recall things from Algebra 2. From Algebra 2. Okay? If I have something that's a 0 in both the numerator and the denominator, what can I do? What can happen? What does that mean for the graph? Mark, did you have an idea? Oh, you're just yawning and stretching. There's a hole, right? When we have a 0 over 0, that's an indication that you found a common, not a common denominator.
I said discontinuity.
Oh, a discontinuity, I'm sorry. Okay, yes, but what kind of discontinuity? A hole, because it's
Jump.
no, it is a hole. So this is gonna be our second thing. So if you get 0 over 0, okay, Emily said that we found a, that was Emily. Not Emily? Are you sure?
Yeah.
The best memory ever. Think back to Algebra 2, a concept that was reinforced to you in pre-calc. What does it mean? You guys spent a lot of time finding zeros in Algebra 2 and pre-calc, right? What are other language? What are some of the other language, or what is some of the other language? Can I speak grammatically correct? What is some of the other language that we use when we're talking about a zero?
X coordinate.
An x-intercept?
Intercept.
Okay, no,
X
but
coordinate.
not in the context of what we're talking about. How do we find x-intercepts? What do we need to find? Like, especially when we're working with crazy
Y
functions?
When you plug in 0 into y.
Okay. A zero, a root, those all come from finding the what of a polynomial function? It's one of my favorite F words.
Functions.
Factors. 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 Okay. So if I have something that's a 0 for the top and a 0 for the bottom, that means that that number is a common, it's like there's a common factor between the two pieces, right? And when something factors out top and bottom, which is what that means is going to happen here, so I'm going to have the limit as x approaches 2. Again, big limit, small x approaches 2, that's a cohesive thing. Sometimes you have like sneaky x things that they just want to be all the way, no. It's all confined here, that's a thing, proper notation is important. What can I do with this? I could factor, one of my favorite F words, x plus 2, x minus 2, over x minus 2, and then what can happen?
Cancel.
Nothing cancels, what happened?
Divide out.
Things will divide out, the x minus 2's divide out to 1, and I'm left with the limit as x approaches 2 of x plus 2. Now, in Algebra 2 and pre-calc, when you divided these out, and you were left with this, and think about what you guys saw earlier in the week with the 5-day walkthrough, if I were to graph this on my calculator, what's it gonna look like?
A line.
A line. What line? That line, right? A line with a slope of 1 and a y-intercept of 2. Except there's gonna be what? A hole. At this thing, where that thing that divided out is 0. Which happens to be a 2, right? Okay? So If you get 0 over 0, you found a whole. Okay? You're going to, what did we do? My favorite F words. Factor. And then what did we do?
Divide out.
We reduced, right? And retake the limit. Okay. So here if I plug 2 in, I'm going to get 4. That's actually really, there's a lot of information right there, guys. Okay. And it's actually a nice way to sum up a lot of what you guys learned in Algebra 2 and reinforced in pre-calc. That I have this crazy rational function. All it's going to be is the line y equals x plus 2. So y-intercept of 2 and a slope of 1. And what does this tell me? Okay, well tell me like what's that going to indicate on my graph?
It's increasing.
All right, the fact that something divided out told us that there was a whole. Okay, what's the significance of the 4?
The actual point is at 2, 4.
The whole, that open circle, is going to be at 2, 4, yeah. Does that make sense to you guys?
Yes.
There's a lot of information in that limit that connects with a lot of what we talked about before. So that means that's my picture. And that picture agrees with that limit. Okay? So if you get 0 over 0, you get a factor reduce and retake the limit. Let's do the limit as x approaches -1 of x plus 1 over x squared minus 2x minus 3. I just want to point out one thing really quickly. I have a fraction function here. I have a rational function. We plugged in our number. We got a number. That was our answer. Just because you're looking at a fraction does not mean that you're looking at a whole. It does not mean that you have to factor and reduce. Okay? It does not mean any of that. So you need to make sure if you plug in -1, what am I getting? You're getting over 0 over 0. And just so that you guys know, 0 over 0 is called something special, and it's a complete misnomer. 0 over 0 is called an indeterminate form. This is something that's we're gonna come back to a couple times over the course of the year. Okay. Indeterminate forms sound like cannot be determined. And that's not what it means. It means do more work. Do more work until you come up with an answer. Okay. So for this one, I get 0 over 0. I'm going to factor, reduce, and retake the limit. So I have my x plus 1 up top. I'm hoping, because I got 0 over 0, I have an x plus 1 on bottom. We can use that to our advantage to do a little less thinking. I'll let you guys sort yourselves. And this is going to have to be an x minus 3. Okay. The x plus 1s are now going to divide out. And I'm going to be left with the limit as x approaches -1 of what?
1 over x minus 3.
1 over x minus 3. Wonderful. Okay. Okay, do you guys see how that x minus 3 was in the denominator? It has to stay in the denominator. We have students every year that are like, screw the fraction, let's just make it x minus 3. No. Okay, if it wasn't a denominator, we're not moving it. And now I can just plug in and get an answer. What's my answer? -1/4. So that means I've got a hole on this crazy mother function at the point -1, -1/4. Okay, remember how you guys were asked in Algebra 2 to find the location of the hole? And it felt uncomfortable? Well, now we actually have a method and a language for it, and it's all nice and neat and in a box, and we can put it on the shelf now. Let's do the limit as x approaches 4 of x squared minus 5x plus 4 over x squared minus 16. again, just because you got a rational function does not mean you're in a 0 over 0 situation, you gotta plug it in. But if you plug it in, you do get 0 over 0, right? So we're gonna factor reduce, retake the limit. So I'm gonna have the limit as x approaches 4. The bottom is lovely. It's x plus 4, x minus 4. Which of these things do you want to maintain in the numerator?
Minus x minus.
The x minus 4, because you want the part that makes it 0 to go away. Does that make sense, guys?
Yeah.
Okay, here's where like deductive reasoning and pattern recognition is helpful. So that's the piece that's going to be the problem. That's where I'm going to have my 0. So I want the numerator also to have that x minus 4. This wasn't that hard to factor, but if it was more complicated, that could help you. What's the other piece was?
X minus 1.
X minus 1. So now these x minus 4s are going to divide out. And I'm going to be left with the limit as x approaches 4 of x minus 1 over x plus 4, and that gives me,
1 over 2.
how about 3 over 8?
2. I do. Alright, yeah, it was tough.
Okay, we're going to get 3/8. And again, graphically, with this crazy mother function, what's happening at 4?
Factor out.
There's a hole. Where's the hole specifically? At what point? 4 over 3. Okay. I'm gonna stop there for today. And your homework's gonna be in your textbook tonight.
Why is it whole like 3